Let's talk about why AI sometimes learns too fast and breaks. So here we'll talk about things like learning rate, instability, and exploding gradients. In the last video, we already came across the idea of vanishing and exploding gradients because of the idea of backpropagation and the fact that several computations have to be done in AI. So errors build up so fast, or and as a result of that, gradients can explode, or you have it going to zero fast enough. So one of the most common reasons neural networks fail during training is that they learn too aggressively. Instead of gradually improving, they make updates that are too large, causing the model to overshoot the optimal solution or even diverge completely. Now, this lesson explains what the learning rate is, why large learning rates cause instability, then how exploding gradients occur. We saw that like in the last video. Then how to detect unstable training, practical techniques for preventing these problems, and the learning objectives are as follows. By the end of this lesson, you should be able to define the learning rate. Of course, we've talked about the learning rate a lot under gradient descent method. Then explain why choosing an inappropriate learning rate causes instability, understand the relationship between gradient descent and parameter updates, identify symptoms of unstable training, and explain exploding gradients mathematically. So apply techniques for stabilizing deep neural networks also. In the introduction, we see that imagine teaching someone to throw darts. Um, After each throw, you tell them how far they missed the target. And these three different behaviors are possible. So imagine a dart. So let me just try to picture it right here. Imagine that you have, let's say this is, so I'll just do something like that. So you have one, two, okay, let me just do it anyhow. I like 5, 6, 7, 8, 9, 10, 11. Okay. Okay, let's just say there you have the goal is to hit 100, right? When you throw when you throw a dart here, you want to hit 100. So let's imagine someone lands here, or someone lands here, or someone lands here, but this is the main place to touch. Let's say this is the main place to touch, right? So, and you know, and one lands here, and you have all the landing all over the place like that. So, of course, this is so far away from here, right? And this is the distance of this from here. This is the distance of this from here. This is the distance of this from here, and so on and so forth. So now, having done all of that, right? Imagine there are three possible behaviors, right? So after each throw, you tell them how far they missed the target. So you can see all the distances. So this is the farthest from the actual place. So from the target. So you can have small corrections. So the person adjusts their aim only slightly after every throw. Each attempt gets closer to the center. Eventually they become accurate, right? But then you can have large corrections. So the person overreacts after every miss, then they miss left, then they compensate too much and miss right. And then they then overcorrect again. They never settle at the target. So small corrections can easily take you to the center, while large corrections will make you miss the target every time. Then you can even have extremely large corrections, right? So every correction is enormous. Instead of improving, the throws become increasingly inaccurate. The person never learns. So neural networks behave in exactly the same way. The learning rate determines how much the model changes after every mistake. So question now is, what is the learning rate? Of course, we've talked about it a lot. The learning rate determines how much the model changes its parameters after computing the gradient. So the parameter update rule is, of course, the gradient descent algorithm. You have the new value of theta is the old one minus the learning rate multiplied by the gradient of the loss function with respect to theta. So theta is a model parameter which you can call a weight. L is the loss function, and eta is the learning rate. So the learning rate acts like the step size in optimization. So small learning rates means taking small steps, while large learning rates means taking large steps. And then we have a quick refresher on gradient descent, which we've talked about a lot. So gradient descent refresher right here. Training a neural network consists of repeatedly performing four steps. You compute predictions, then you compute the loss, then you compute the gradient and update the parameters. The parameter update equation is W new equals W old minus the learning rate multiplied by the gradient. So, I mean, where G is the gradient, the LDW. The gradient tells us which direction to move and how steep the loss surface is. The learning rate determines how far we move in that direction. So, I mean, in some videos, I already give the example of moving on a mountain. You want to get off a mountain with your eyes blindfolded. So, each step you take either takes you up or down. So, how do you know you're going up? You feel you have to exert more energy to go up. So, to go down, you can, if you are not careful, you don't need to exert so much energy, but you can easily slip off. So that way, you have to take very manageable steps to get off carefully. So the current weight, for instance, let's assume it's W equals 5 and gradient is 2, the learning rate is 0.1. So it means that the new W will simply be 5 minus the learning rate times the gradient, and that will be 5 minus 0.2, which is 4.8. So the weight changes only slightly from 5 to 4.8. So this small adjustment helps the model move steadily toward the optimum. And then they talk about the effect of different learning rates. Suppose the optimal weight W is 0 and the current weight is 10 and the gradient is 10 also. We will examine three different learning rates. So imagine a small learning rate of 0.01. Eta is 0.01. So the update becomes 10 minus 0.01 times 10. That is 10 minus that's 10 minus 0.1, right? So if you knock off 1 0, that's 1. If you knock, so next step will be 0.1. So 10 minus 0.1 is 9.9. The model moves only a small distance towards the optimum. So because you are still going towards 0 and you're at 9.9, that's really slow. So training is slow, but it is actually stable. Now let's go for case 2, where you have just moderate learning of 0.2. So the update becomes 10 minus 0.2 times 10, which is 10 minus 2, which is 8. The model moves faster while remaining stable, and this is generally feasible. Now come and see this other one. Suppose eta is 1.5 now. Then 10 minus 1.5 times 10 is 10 minus 1.5 times 10 is 15. So 10 minus 15, that's minus 5. In fact, you have jumped over 0 to minus 5. So this model has jumped completely past the optimum, which is 0. And the next update becomes minus 5 minus 1.5 times this. You have 2.5. So you have jumped to the other side positive again. So the following update becomes 2.5 minus this. Now you have jumped to the left, which is minus 1.25. So instead of converging, the parameters oscillate around the optimum. And this behavior is called overshooting because the learning rate is too high, like that. So it's more like you're just jumping all over the place. In example 2, if you consider the simple loss function L of W equals W squared, its gradient is 2W. Suppose W is 8. We compare several learning rates. Of course, for W squared, this is basically a parabola that faces upward with a minimum value at W equals 0. So we are hoping that we want to get to 0, basically. So let's see how the learning rates perform in that direction. So for learning rate 0.1, so for iteration 1, now the gradient is 2 times 8, which is 16. To update, you have 8 minus 0.1 times 16, which that gives you 6.4. For iteration 2, you now have 2 times 6.4, that's 12.8. So 6.4 minus 0.1 times 12.8, you have 5.12. So it's dropping steadily. Iteration 3 gives 4.096. Now this wave smoothly approaches 0 because we have a learning rate of 0.1. Imagine a learning rate of 1. What does it do? For a learning rate of 1, iteration 1, you have 8 minus 16, that's minus 8. Iteration 2 minus 8 plus 16, 8. So you see it's just jumping all over the place. Iteration 3 is 8 minus 16, you have minus 8. The parameter never converges. Instead, it oscillates forever because we have a learning rate that is actually not making sense. Then imagine learning rate of 2. Probably that's even worse. Iteration 2, 8 minus 32. Iteration 1, 8 minus 32, you get minus 24. Then iteration 2, minus 24 plus 96, that's 72. Iteration 3, 72 minus 288, that's minus 216. So, I mean, 0 is the actual optimal solution, and these ones are nowhere near that 0. So the values become increasingly larger, and the training has diverged already. Of course, here, at least you have this one jumping. So from minus 8 to 8, 0 is somewhere in the center. From 8 back to minus 8, 0 is somewhere in the center. But here, 0. Okay, well, I mean, you still have 0 somewhere, but the distance is just so far apart. So we can actually have the different learning rates here and see how they behave. So imagine if you run this, so you see for learning rate 0.1, that is stable and it's just going along the zero. 1.0 also tries to behave a bit close, but the other one, learning rate of 2.0, you see, it behaves, just keeps, it becomes haphazard at some point, so at some iteration, so like that, um, for the same function, W squared. So then, why large learning rates cause instability? Imagine walking down a mountain. If you take small steps, you gradually descend toward the valley. If you take giant leaps, you repeatedly jump over the lowest point. This is exactly what happens during optimization. So, I mean, this is the scenario we're trying to paint here. Uh, Imagine you have a mountain, a valley, a mountain like this. And say, let's say this is the lowest point of the mountain. So if you take small steps, you can gradually come down like this. But imagine you are always jumping. So you jump from here, you take too wide a jump, you come here, then you jump again, you come back here. You jump, of course, even here, if you now repent, right? If you now change your mind and start coming down, you can still make it down here, right? But if you just keep jumping, you keep missing the minimum point. That's the idea of, very big learning rates. So if you take giant leaps, you repeatedly jump over the lowest point. This is exactly what happens during optimization. Large learning rates produce updates that are too large. Instead of reducing the loss, the optimizer repeatedly overshoots the minimum. As a result, the loss oscillates, the parameters fluctuate, training becomes unstable. And the question is, what is training instability? Training is said to be unstable when the optimization process no longer moves consistently toward a lower loss. So instead of improving steadily, the model behaves unpredictably. And common symptoms include things like rapidly increasing loss, oscillating loss, unstable accuracy, very large parameter values, numerical overflow, not a number values, infinity values, infinite values where you have infinity, and then you have complete divergence like that. So, and that brings up the idea of exploding gradients like we saw in the last video. Now, during backpropagation, gradients are propagated backward through every layer. If these gradients become larger at each layer, the final gradient becomes enormous. Instead of making small updates like from 0.4 to 0.5 to 0.6, you can then have the optimizer suddenly producing updates such as 100 to 5,000 to 200,000, very insane jumps like that. So such massive updates immediately destabilize training. So this phenomenon is called exploding gradients. Now, why do exploding gradients occur? It is because of backpropagation, right? Suppose gradients are multiplied repeatedly during backpropagation. So if each layer contributes the factor 3, so then after 10 layers, you have 3 raised power 10, which is 59,049. After 20 layers, it has jumped seriously. You have 3 raised power 20, that's approximately 3.49 times 10 raised power 9. The gradient grows exponentially with depth. So very deep networks are therefore especially vulnerable to exploding gradients. So imagine example 3 here. Suppose you have layer 1 gradient to be 2, layer 2 be 2 raised power 2, 2 raised power 2, that's 4. Layer 3, okay, you have 2, 4, 5. In layer 3, you have 5. So the final gradient then becomes 2 times 4 times 5, which is 40. Now, if the learning rate is eta, which is 0.5, the parameter update becomes 0.5 times 40, which is 20. A single update changes the weight by 20 units. So such a large jump usually causes the optimizer to overshoot the optimum value like we saw in previous examples. So imagine here that you have a gradient of 1.0 and you're printing the layer and the gradients like this. So for layer in gradient from 0 to 9, that's range 10 now, 0 to 9. So that's 1 to 10. So you have the gradient. So to update, right? So you have for gradient 1 now. So for gradient 1, you have 1 times 2, you get 2 here. So what this line means is that each gradient is updated by multiplying by 2. So next, at gradient 2 now, you have 2 times 2, that's 4. At gradient 4 now, 4 times 2, you get 8. And it keeps going. At 10, you have 1024. And it just keeps going like that, just being so big. Now, how do you detect exploding gradients? Signs of exploding gradients include rapidly increasing loss, extremely large gradient norms, enormous parameter values, NAN losses, infinite values, sudden collapse in validation accuracy. Now, monitoring gradient norms during training is an effective way to detect this problem. So, in that case, you need to import torch. So for name and parameter in model.named parameters, if parameter grade is not known, print name and all that. So here by writing this line of code, you can easily detect gradients. So the ones that are not available will be shown as none. Otherwise, you print the ones that do not have that idea of excluding gradients. So now question, let's talk about preventing instability. Several techniques can stabilize neural network training. Now use a smaller learning rate. Instead of LR to be 1.0, you can use LR to be, that's learning rate to be 0.001. Smaller updates now reduce overshooting. That's one thing. That's one way to prevent instability. Another thing is, so you can prevent instability by using smaller learning rates. Number two, you can do gradient clipping. So you limit excessively large gradients before updating the parameter. So any gradient that goes beyond a particular range, to the right or to the left, you skip it, you avoid it. So imagine saying maximum norm is 1.0. So anything that departs from 1.0, it's removed. Then you can also do better with initialization to manage instability. So methods such as Savia initialization and He initialization help maintain stable gradients. Then you can do batch normalization. So batch normalization keeps intermediate activations within reasonable ranges, improving optimization stability. Then five, you can have adaptive optimizers. Algorithms such as Adam, RMS prop, and AdaGrad automatically adjust effective learning rates for individual parameters. And six, learning rate scheduling. Reduce the learning rates gradually during training to improve convergence. So in summary, we see that very small learning rates results to stable but slow behavior. Moderate learning rates is fast and stable. Too large leads to oscillation. Extremely large leads to divergence. So you never converge to the optimum solution that is expected. That's what happens in that regard. So exploding gradients are another major source of instability in deep learning. So learning rates, then exploding gradients. So fortunately, techniques such as gradient clipping, better initialization, adaptive optimizers, and learning rate scheduling make training much more stable. Choosing an appropriate learning rate is one of the most important decisions when training neural networks. So, and then we have the practice problems. So solve the following problems without referring to the worked examples in the lesson. Of course, as usual, I get to solve two of this. So right now you can see questions 1 to 5 very clearly. So I'll be solving 7 and 18. So you can see problems 1 to 6, in fact, with this. Questions 1 to 6. Then question 7 is the first one I'll be solving. Suppose the gradient doubles at every layer of a deep neural network. If the gradient entering the first layer is 0.5, what is the gradient after 8 layers? So that's the first problem I'll be solving. Then so from here you can see questions 7 to 14 all together, 7 to 14. Then 7 to 14, right? Then 15 to the end. So you can see the rest now. So the other problem I'll be solving is problem 18, which says a model begins training with a learning rate of eta equals 0.02. Every 10 epochs, the learning rate is multiplied by 0.5. What will the learning rate be after 30 epochs like that? So we have to take care of these problems. So we have problem 7, problem 7. Problem 7 says, suppose the gradient doubles at every layer for a deep neural network if the gradient entering the first layer is 0.5. What is the gradient? What is the gradient after 8 layers? Okay, so we have the solution. So you have the gradient. The gradient is multiplied by 2 at each layer. So, and we have the initial gradient to be G0, which is 0.5. So after one layer, we have G1 to be 0.5 times 1. So after two layers, we have G2, which is, oh, this is 0.5 times 2, right? Sorry, this is 0.5 times 2, which is equal to 1. So after two layers, we have 1 times 2, and that is equal to 2. So continuing the continuing the process, we then have G3 to be 4, G G4 to be 8, G5 to be 16, G6 to be 32, G7 to be 64, and G8 to be 128. So it's 128 after 8 layers. So that's one way to go. Alternatively, right? Alternatively, you can do some quick math thing. This is basically geometric progression. So alternatively, we know that G8 should be 0.5 times 2 raised to power 8. So that means G8 is equal to 0.5, and 2 raised to power 8 is 256. So G8 is equal to 128, and that goes. So what do we say here? So this example, the answer is 128, right? This example illustrates how gradients can grow exponentially in deep networks, eventually producing extremely large parameter updates. So we go on to problem 18. So a model begins training with a learning rate of eta equals 0.02. Every 10 epochs, the learning rate is multiplied by 0.5. What will the learning rate be after 30 epochs? So, and here the solution is this. So we know the learning rate is reduced every 10 epochs. So we say that after after the first 10 epochs, eta will be 0.02 multiplied by 0.5, and that is 0.01. Then, after 20 epochs, we have eta to be 0.01 times 0.5, that is 0.005. Then after 30 epochs, eta then is 0.005 times 0.5, and that is 0.0025. So, I mean, we can also also compute directly. We can also compute it directly. So eta final will just be the initial value, which is 0.02 times increase. So after 30 epochs, that's the third increase, right? So that way, eta final will be 0.02 times 5 times 5 times 5, that's 125, that's 0.125, actually 0.125. So that eta final is equal to what we have, the same results that we got up there, that's 0.0025. So this is 0.0025. And that's the final answer. So this is an example. This is an example of learning rate schedule. So you can do learning rate schedule. So that's one way to make sure that there's stability. This is an example of learning rate schedule. Learning rate schedule where the optimizer, takes progressively smaller steps as training proceeds. So we see that large steps help the model learn quickly at the beginning, while smaller steps later help it converge more smoothly. So that's one technique there, learning rescheduling. So you start with large steps so you can move fast, but after some time, after some epochs, you make it smaller and smaller so there can be smoother and smoother convergence. So and that's one technique to avoid instability, to prevent AI from learning too fast such that it breaks. So again, look at the problems. So here you can see 1 to 5. Solve the following problems without referring to the worked examples in the lesson. Unless otherwise stated, use the gradient descent update rule. W new equals W old minus eta dl dw, like that. Then you can see 6 to 10 here. Then 11 to 15. And finally, you have 16 to 20. I already took care of, I think, problems 7. I did problem 7 and, of course, 18. like that. So try your hands on the rest and see how well you get the gist. If you have subscribed to this channel already, I thank you very much for doing this. If you have not, why not go ahead right now and subscribe and of course hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you special privileges as you are going to see when you click on join. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.